Reusable rockets are supposed to make spaceflight cheaper, and that's the headline everyone knows. What the headline leaves out is that a rocket which lands is not the same as a rocket that's ready to fly again, and the gap between those two things is where the actual economics play out. This video covers refurbishment, what it costs, what it used to cost, and why the speed of turning a booster around matters more than almost any other number in the space business. Start with a number that defined spaceflight for decades. The shuttle's average cost, when you divide the total program spend across all 135 flights, came out to roughly $1.5 billion per launch. It flew to orbit and came back. The orbiter landed on a runway. The main engines were recovered, reinstalled, and flown again, and yet the per-launch cost ended up higher than many fully expendable rockets of the same era. Between flights, the shuttle required 10,000 contractors and 1,000 civil service personnel just to process it, and the main engines alone carried a design target of 55 reuses that consumed extraordinary time and money to chase. Dan Dumbacker, former NASA Deputy Administrator for Exploration Systems Development, put it plainly in 2014. "We tried to make them reusable for 55 flights. Look how long and how much money it took for us to do that, and you still weren't completely successful for all the parts. I want to be realistic. We are not as smart as we think we are." The shuttle didn't fail at reusability because NASA lacked skill or will. Nobody had yet answered the fundamental question: what does refurbishment actually need to cost for the economics to close? SpaceX came at this differently. The original Falcon 9 cost roughly $300 million to develop, while NASA's own cost model estimated the same work would have run $3.6 billion under traditional contracting. That gap came from vertical integration. SpaceX handled design, manufacturing, software, testing, and operations in-house, calculating that subcontracting $1 of work externally would cost $3 to $5 once overhead and profit were added. Developing reusability on top of that rocket cost SpaceX at least another $1 billion, which Musk acknowledged at the March 2017 press conference after the first Falcon 9 reflight. We do have to figure out some way to pay off the development costs of reusability. Two debts from the start, and the only way to retire both of them is to fly often. By around 2022, refurbishing and reflying a Falcon 9 first stage cost approximately $1 million, down from an estimated $13 million just 5 years earlier. And that drop is one of the most consequential cost reductions in the history of aerospace. On December 21, 2015, the first Falcon 9 booster landed vertically at Cape Canaveral, and SpaceX chose not to refly it. The stage went through inspection, completed a static fire test, and ended up on permanent display outside company headquarters in Hawthorne, California. That decision reveals what a recovered booster was actually worth in 2015, which was not primarily the hardware. The real value was the data. What re-entry had done to the engines, where wear had concentrated, and what turned out to need no attention at all. The first reflight came in March 2017, roughly 11 months after booster B-1021 made the first ever drone ship landing on April 8, 2016 on the CRS-8 mission for NASA. Getting that booster ready again required full disassembly, engine removal, a trip back to the Hawthorne factory, reassembly, and a separate test campaign in Texas. Not rapid reusability, careful reusability, because the engineers were still building the knowledge base they'd need to trust this hardware commercially. Block 5, introduced in May 2018, redesigned the heat shield, engines, and grid fins around rapid reuse as the default assumption rather than the exception, and the results came fast. Between 2021 and 2022, average turnaround dropped from 27 days to 21 days. By March 2025, booster B-1088 flew back on Enroll 57 just 9 days, 3 hours, and 39 minutes after landing from the NASA Sphere-X mission, then flew a third time inside 23 days from that first launch. Gwynne Shotwell had set the real benchmark years earlier. Our challenge right now is to refly a rocket within 24 hours. That's when we'll really feel like we've got reusability right. That target hasn't been reached yet, but the trajectory is unmistakable. SpaceX has now landed Falcon 9 boosters more than 600 times, and every recovery added to the knowledge base. The shuttle flew 135 times over 30 years, a pace that never allowed the workforce to shrink because confidence in the hardware never got high enough to reduce oversight. SpaceX flew 165 times in 2025 alone, and that cadence, more than any single design choice, is what eliminated the large maintenance crew. When you understand the failure modes well enough to design them out, you stop paying people to search for them. There's a point on the cost curve where refurbishment stops being the constraint. The rocket still needs maintenance, but launch pad availability, payload manifest, and regulatory scheduling become the actual limits. SpaceX is operating close to that point now. In 2024, SpaceX completed 134 Falcon launches, more than half of every orbital mission flown anywhere on Earth that year, with the combined output of every other provider worldwide still falling short of that total. Booster B1067 has flown 34 times, against a reused Falcon 9 cost of roughly $800 per kilogram to orbit. United Launch Alliance's Vulcan Centaur opens at $110 million per launch. Ariane 6 runs $77 to $115 million with every component discarded, and Rocket Lab's Electron costs over $19,000 per kilogram. Blue Origin's New Glenn is the most credible challenge. Designed for a minimum of 25 flights per booster and priced at $68 to $110 million per launch, it landed its booster at sea on November 25, 2025, making Blue Origin only the second company to recover an Orbital-class booster. What followed, though, is the honest measure of where they sit on the learning curve. Engineers replaced all 7 BE-4 engines on the recovered stage, keeping only the outer structure, and the first reuse came in April 2026, roughly 5 months after landing. That's where SpaceX stood in 2016 and 2017, and closing that gap requires flights and data, not a single engineering breakthrough. Starship is the next variable that reshapes the whole equation. Both stages return and land. The Raptor engines burn liquid methane, and in August 2025, SpaceX introduced a redesigned Raptor with part count reduced by nearly 30% through 3D printing, targeting production of up to 300 engines per year. The stated launch cost goal sits under $10 million per mission, against a current Falcon 9 list price of $74 million. If that target is reached, the cost per kilogram to orbit could fall below $100, down from $54,500 on the shuttle and $2,720 on the Falcon 9 today. As of mid-2026, Starship has completed 11 test flights with a program pause following a June 2025 test stand explosion. Those targets are goals, not guarantees.